Hi folks, so in this part of the lesson we're going to take a look at some examples on operating with algebraic vectors. Alright, now remember that we saw that we could multiply by a scalar by just multiplying the individual components by that scalar. We can add and subtract vectors by just adding and subtracting the individual components, and that things like distributivity and commutativity, those all still apply. All right, so let's take this here. Let's say we take 2u minus 3v. So the first thing I'll do is I'll write out the vector as it's given. So u is negative 5, 3, 2. And then here minus 3 times vector v, which is 2, 1, negative 7. All right, so the first thing I'm going to do is I'm going to apply the scalar multiplication to both of these vectors. So here we said that we multiply by a scalar by just multiplying the individual components. So this first operation is going to give me negative 10. 2 times 3 is 6. 2 times 2 is 4. Okay, minus, and here I'll multiply out the 3. So 3 times 2 is 6. 3 times 1 is 3. And 3 times negative 7 is negative 21. All right, so now that we've taken care of the multiplications, we can go to the subtraction, and we saw that we could subtract vectors defined this way by just subtracting the individual components. So here we're going to do negative 10, minus 6. Okay, forget that. Here we have 6 minus 3, and then finally we have 4 minus negative 21. All right, so we see here how much easier it is to do the subtraction operation using algebraic vectors than if we were working with geometric vectors as we did previously. So our final answer here will just be negative 10 minus 6 is negative 16, 6 minus 3 is 3, and then 4 plus 21 is 25. Okay, now normally if you would be doing a question like this, I would probably expect you to skip certain steps. I wouldn't expect to see this step for sure. Having said that, I don't know that I would want to try to write the final answer right off the bat. All right, so let's move on to the second question. It says write 6, 3, 4. So again, another 3D vector in terms of the standard basis vectors. So remember that our standard basis vectors, so in 3D, we call them I, J, and K, and we use little hats. And what those represent are they represent the unit vectors in each of the positive directions on the axes. Okay, so if this is x, y, z, this would be 1, 0, 0 would be vector I, this would be 0, 1, 0, this would be vector j, and this here would be 0, 0, 1 would be vector k. All right, so if I want to write that out, so normally I wouldn't write this first step, but this is just to make sure we see how it does make sense to write what I'm going to write at the end. Okay, so I'm going to write this vector as 6 times the vector 1, 0, 0. So that just gives me 6, 0, 0. And then I'm going to add to that 3 times the vector j, which is 0, 1, 0, the one in the y direction. So this gives me 0, 3, 0. And then I'm going to add 4 times the k basis vector, which is 0, 0, 1, which is going to give me 0, 0, 4. And so when we add all of these together, I just end up with 6, 3, 4. But in order to write this in a simpler way, we're going to use our notation here. So this can just be written as 6 times vector I plus 3 times vector j plus 4 times vector k. So in other words, whatever the components are, the first one x times vector I plus the second one times vector j plus the third one times vector k. All right. Now, for our purposes, we're going to be working with this representation of an algebraic vector, but certainly you can write it using the standard basis vectors too. All right, let's move on to the next one. So this asks us to write 10, negative 5 as a linear combination of these two vectors. Okay, now when I wrote this expression here, it was a linear combination of vectors I, j, and k. What does a linear combination mean? It means I can multiply the vectors by scalars and I can add or subtract them. Okay, so essentially we're going to be using 2, 3, and 4, 1 as basis vectors. okay? Because we're going to use them to write another vector in this case here, 2D. Now notice these are definitely not horizontal and vertical, and I think you can see pretty quickly that they're not unit vectors, but basis vectors are not necessarily unit vectors, and they're not even necessarily perpendicular. All right. Now, before we actually go and do the work here, how do I know for sure that I can do this? Well, remember what the condition was for vectors to act as basis vectors in R2. Neither of them can be 0, which obviously neither of them are, and they can't be parallel to each other. So if I look at these two vectors, it's clear they're not scalar multiples of each other, so I know that this should work. Okay, so the way I'm going to write that here is I'm going to pick letters to represent my scalar multiples. So let's say I use P and Q. So what I want to do is I want to multiply 2, 3 by some scalar multiple, say P, and then add that to some scalar multiple of 4, 1. Okay, and that is going to give me the vector 10, -5. So this is what I'm solving in order to answer this question, is what linear combination of 2, 3, and 4, 1 is going to add up to 10, -5. Okay, so I'm going to start by simplifying the left-hand side so I can get one vector on either side of this equation. So here, scalar multiplication, so that's just going to be 2p and 3p, because I just multiply p to the individual components. Do the same thing here with q, so that's going to be 4q and then q. Nothing to do yet on the right-hand side. So now let's keep simplifying. Let's add these two vectors together. So now I just add the individual components. So 2p plus 4q, and this is going to be 3p plus q, and all of that is going to equal to 10, -5. So now I have these two vectors that are equal to each other. That must mean that the x components are the same. So 2p plus 4q has to be equal to 10, and the y components have to be the same. So that means that 3p plus q has to equal to -5. And this is where I realize that I have a system of equations. All right, two equations and two unknowns, so I know how to solve that. I'll use elimination here to do that. So let's eliminate the q's. So I'm going to multiply the second equation by 4. So 4 times equation 2 is going to be 12p plus 4q is equal to -20. And here I'm going to subtract them in order to eliminate the q's. Okay, so 2p minus 12p is -10p equal to 10 plus 20 is going to be 30. So that means p is equal to -3. And then I'll use equation 2 to solve for q. Okay, so 3 times p, which is -3 as I just found, plus q is equal to -5. So q is equal to -5, and this is -9. Bring it to the other side, so plus 9. So q is just going to be equal to 4. So what does that tell me now? That tells me that my vector 10, -5 can be written as a linear combination of those other two vectors. It's going to be equal to -3 times vector 2, 3, because that's what I multiplied by p, and then plus 4 times vector 4, 1. And of course, as you can always do with a system of equations, is just check your answer. So let's check what we have. We have -6 plus 16 is 10, and let's check the y values. -9 plus 4 is -5. So there we go, the right answer. All right, let's move on to number 4. So here they're not asking us for much, they're just asking us for the vector that joins point A to point B. All right, so just as a reminder how we do that, so here we're in 3D. Now I'm not going to make an effort to draw this exactly, it's just to indicate how I solve this. If I have point A and I have point B here, and I want to find the vector that joins them, I think of it as not the point A, but the vector OA if O is the origin and the vector OB, and then I recall, yes, of course, when I have two vectors tail to tail and I'm joining their tips with a vector, it's a subtraction. So from the tip of the second to the tip of the first. So that means that my vector AB is just given by OB minus OA. Okay, so that it's the tip of the second to the tip of the first. All right, and so what's that? OB is just going to be -3, 1, -5, minus OA is 2, 3, 7. So here we end up with -3 minus 2 is -5, 1 minus 3 is -2, and -5 minus 7 is -12. All right, so there's the answer. The vector going from A to B. It's just about subtracting the second minus the first. All right, so these were all relatively straightforward. Number 3 required a little bit of work, okay, but nothing too complex. Let's take a look here at number 5, A and B. This is a little more, let's say, a little more interesting question here. Okay, but we're just going to use all the tools that we have. So it says find the point or points on the y-axis which is equidistant to the points 2, -1, 1 and 0, 1, 3. All right, so let's give these points names. Let's say I call this A and I call this B. So now, again, I'm going to draw a diagram. However, I am going to draw it with an axis, with a set of axes here. But again, I'm going to make no effort to be exact. Okay, I definitely don't want to have to try to draw these points exactly in R3. It takes a long time, and it's usually not very helpful visually. Okay, but I do think it's still worth drawing a diagram. So the first thing I want to do is I want to find a point on the y-axis. So if this is my point on the y-axis, I have to ask myself, what's special about a point on the y-axis? And I realize that, well, the z component is 0, and the x component is 0. Okay? On the y-axis, we see I don't go either front or back in the x direction. I don't go up or down in the z direction. Those are both equal to 0. So what I'm going to do is I'm going to identify this point as 0, y, 0. I'll call that point capital Y. Okay? And what's special about this point is that it needs to be equidistant to these 2 points. So let's say I call this A, and let's say I call this B. And the distance from A to B, and the distance from A to Y, and the distance from B to Y has to be the same. So I'll call this D1, I'll call this D2. I need D1 to be equal to D2. Okay? Now the question is how do I find the distance between 2 points in R3? Okay? Well, I could try to come up with a formula, but I think we have a way of doing that because I realize that the distance from A to B is the same as the magnitude of the vector joining these 2 points. So instead of coming up with a separate distance formula, I'm just going to create a vector from A to Y. Now I'll talk about in a second why I did A to Y and not Y to A. Okay, and I'm going to do the same thing here. Create a vector from B to Y. And distance D1 is just the same as the magnitude of the vector AY. And D2 is just going to be the magnitude of the vector BY. And those two have to be equal. All right? So let's calculate the vector AY. And I think you'll see in a second why I chose this direction and not the other. Okay? So remember how we find the vector joining 2 points. It's the second minus the first. So the second, if we're ending here, minus the first. Okay, so 0 minus 2, -2. Y minus -1, so y plus 1. And then here, 0 minus 1, -1. Okay, and this is where I can tell you why I chose to go in that direction. Because I'd much rather have y plus 1 than going in the other direction, -1 minus y. It's not a big deal, but anytime I'm solving, I always like having the variable come first. Okay, and that's really the only reason why I chose AY instead of YA. And you'll see something similar here when I do BY. Okay, so 0 minus 0, that's just 0. Y minus 1, again, the variable comes first. And then 0 minus 3, negative 3. Okay, so now I have these two magnitudes. Let's calculate them. So the magnitude of the vector is given by the sum of the squares of each component. So negative 2 squared plus y plus 1 squared plus negative 1 squared. Okay, on the other side, we've got 0 squared plus y minus 1 squared plus negative 3 squared. Okay. Now I have these square roots on either side, so I might as well just square both sides. Make it nice and easy. So here, square roots disappear. Let's start simplifying the inside. So negative 2 squared is 4, plus, let's expand this. It's going to be y squared plus 2y plus 1, plus negative 1 squared is 1. And here, the 0 just goes. So I have y squared minus 2y plus 1, and then here plus 9. And this is where we see something very nice happening. The y squareds just cancel out. You can just subtract y squared from both sides. In fact, this one cancels out with that one. So if we start to do a little simplifying here, well, let's bring all the y's to one side. So 2y plus 2y, we have 4y. And then here, what do we have? Well, we're left with a 9, and then we'll bring the 4 minus 1. So we just end up with 4y is equal to 9 minus 4 is 5, minus 1 is 4. And there you go, nice and easy. Y is just equal to 1. Okay, so what does that tell us? Our conclusion here is that we have only one point, okay, which is equidistant to the points A and B. So the point 0, 1, 0, because remember it was our point on the y-axis, is equidistant to A and B. All right? So in part B, we have a very similar question, except now I've taken away the condition. Remember here we had the condition that the point I was looking for had to live on the x-axis, on the y-axis. Here, it can be any point. So I'm going to draw my diagram again, except I'm going to take away that condition. So I'll call this A, I'll call this B. Now, it might be tempting to, put my point here. It's equidistant to A and B. Remember, you always want to try to avoid drawing the special scenario, because I figure, hey, this point here is also equidistant to A and B. Okay? So again, D1, D2, still the same distance. So here now I'll call my point, instead of being precise about the x and y components, it could be any point in 3D. Okay? So I don't have that condition anymore on x and z. Okay? But like I did before, if I'm trying to calculate these distances, I'm just going to calculate them as the magnitudes of the vector A to P and B to P. Okay, and again, notice I go A to P. When I do second minus first, my variables will always be the ones that come out first in those subtractions. All right, so I still want D1 equal to D2. D1 is going to be given by the magnitude of the vector AP, and D2 is going to be the magnitude of the vector BP. Okay, and you're going to see what I do now is going to be very similar to what I did before. Okay, let's start by, actually, I guess before I take the, let me show this step by step. I was almost going to do it in one step, but let's do it step by step. First, find the vector AP. Okay, so the vector AP again, so second minus first, so x minus 2, so x minus 2, then y minus negative 1, y plus 1, z minus 1. Okay, and let's find the vector BP, x minus 0, here y minus 1, and then z minus 3. Okay, So now that I have the two vectors, I can take their magnitudes. So this is going to be square root of x minus 2 squared plus y plus 1 squared plus z minus 1 squared. This is going to be the square root of just x squared plus y minus 1 squared plus z minus 3 squared. Okay, same as before, square both sides to get rid of the square roots. Okay, and let's start expanding here. So we have x squared minus 4x plus 4 plus y squared plus 2y plus 1 equals z squared minus 2z plus 1. And then here we have x squared plus, well, again, expanded binomial, y squared minus 2y plus 1, and then z squared plus 6z plus, oh, sorry, I just realized that's z minus 3, not z plus 3, so that would be minus 6x. Okay, always good to keep looking above to make sure you catch any silly mistakes like that, and that'll be plus 9. But hey, similar to what happened before, x squared and x squared disappear, y squared and y squared disappear, z squared, that should have been a plus, z squared and z squared disappear. So let's collect all the variables to one side. So it looks like we have negative 4x, no other x here, so negative 4x. But here we have 2y plus 2y, that'll be plus 4y. Here we've got negative 2z plus 6z, so plus 4z equals, so what do we have on the right-hand side? 9 plus 1 is 10. And then here, well, we've got a plus 4, bring it to the other side, minus 4. And then 2 plus 1s, so let's subtract them to the other side. And so what do we have? Negative 4x plus 4y plus 4z is equal to 6 minus 1, that's equal to 4. And look what I have here. I have a single equation with these three unknowns. So that means I can't solve for one particular solution. In fact, let's simplify this a bit. I've got all these 4's hanging around. Let's divide both sides by, say, negative 4. So what do we end up with here? We end up with x minus y minus z equals negative 1. So again, I have this equation with these three unknowns. So that means there's more than one solution. In fact, when you think about it, this must be telling me that there's infinitely many solutions, because I could come up with a whole bunch of trios that add up to negative 1 here. Let's say x is 6 and y is 1. So 6 minus 1 is 5. And then let's make z equal to 6. 5 minus 6 is negative 1. There you go. There's one triple. You know, x could be equal to 10, and y is 4. 10 minus 4 is 6. Minus 7, make it z equal to 7. That's also equal to negative 1. So you can see that you can come up with infinitely many solutions. Okay, therefore the answer is given by, well, any point x, y, z such that x minus y minus z is equal to negative 1. So that means there's infinitely many solutions to this question here. Now, if you think about it, not too surprising that you can find lots of points that are equidistant to A and B. So one thing that I might leave you with is, what do all such points represent? Try to think of it physically. What would they all represent? And we're going to see that we're going to come back to this exact same question in a couple of weeks probably. All right. So that's it for this. There's just lesson 3 coming up.